Now imagine this. It is 2005, the year 2005, and you are a software engineer and you work basically at a e-commerce based company, and the company is rapidly growing because it's 2005, because of the dot-com bubble, etc., etc., right? The company is rapidly growing, and you have a task. You are a software engineer and you have a task to search through thousands of products. Your company has around, let's say, 5,000 products, and you have to write a database query to create an API which searches, given a user input, searches through your database and returns some relevant results, right? And this is how you write the query for that in a typical relational database based setup. You say select star from products, where name is like laptop, so these percentage symbols are for matching any characters that comes before and comes after that. Either it can match name or it can match description. If the keyword laptop is either in name or in description, you return those results, right? This is how you do a basic search, and the customers search for laptop, they get a few results, and life is very simple. Now something happens. Since it is 2005, and because of a lot of companies' growth, your company also grew, and it grew rapidly. Suddenly you had millions of products, right? The very straightforward I like and the percentage symbol based search in your relational database query that once returned results in, let's say, 50 milliseconds, now it is taking 30 seconds. And because of that, your customers are frustrated, your manager is frustrated, and everyone is asking you to optimize it, and you are clueless. They don't just want to make it faster, they also have more requirements like, can we make the search smarter? For example, when someone searches for laptop, you want to show the most relevant results faster. For example, let's say someone searches laptop, instead of showing a laptop bag, we want to show a MacBook Pro first, right? So that kind of smart searching, relevance based searching. And we also have a requirement that customers are there in a hurry during the sale time, right? So instead of writing laptop, they are writing laptop pretty frequently, and we also want to take that into account. Even though they make typos, customers make typos in their user queries, we still want to return relevant results for laptop instead of laptop, right? We want to make it faster, we want to make it relevant, and we also want to be robust enough that typos cannot break us. And with all these requirements, this is the story of why search engines like Elasticsearch came into place, because of all these requirements. And this is what we are going to talk about. To get the intuition of it, your Postgres database or whatever relational database that you are using, now that database is like a librarian. You go to a librarian and you ask a librarian the locations of different books or different categories, right? So your Postgres database is like a librarian who knows exactly where every book is located. But it has one fatal flaw. We have our librarian here. If you ask the location of a random book, then to find that book, the librarian has to look through every single book in every single shelf in the whole library, one by one. That is its fatal flaw. So for example, let's say you ask for a book called machine learning. You go to the library and you ask the librarian that I am looking for books about machine learning, right? So the librarian starts its search. It finds the first book. The first book's name is Harry Potter and the Philosopher's Stone, and it checks that no, there is no machine learning in this. Moving on. Then it finds that Game of Thrones. Again, there is no machine learning in that title. Moving on. Then it finds a book which is called Introduction to Machine Learning. Finally has a match and it returns that. Now that librarian will continue this process of going through every book one by one in the whole library. Depending on the size of the library, it might take a few minutes to a few hours, in fact a few days if it's a huge library, right? Let's say a library with 10 million or 1 billion books. That is one thing, the time it takes to find all our books. The second thing is the librarian has no concept of relevance. And what do we mean by relevance? In the sense that if the librarian finds two books, in one book, the the name of the book is an introduction to machine learning, and in another book, the phrase machine learning is just mentioned in the last page, and the topic is something else, but machine learning is just mentioned there. And it returns both of these books in any order it wants, right? It can return the second book, which only has machine learning in the last page, which is not very relevant, and it can return that book first and return the book named An Introduction to Machine Learning second. Even though if you're asking for books about machine learning, we want the first book, which is titled as An Introduction to Machine Learning first, and we might not even want the second book because it is pretty irrelevant in our use case. Coming back to our databases, if you think about the librarian, the example that I talked about just before, as our database itself, then a query like this, where we use I like, which is basically a case insensitive search and using percentage symbol. This is exactly how the librarian looks for books in a huge library. The database has to scan every single row, examine every single text field, and perform pattern matching character by character. Now it is thorough. It is going to return results that are matching, but it is painfully slow. And second thing, the relevance thing, it does not really know which results are more important than others. It returns them in a random order. We might want some results might be completely irrelevant, and some results might be very relevant, but they might be in the position of, let's say, 1,000 or 10,000, right? The database has no sense of what is the most relevant result. Okay. Now coming back to our history, since we are talking about 2005, around the same time, the information explosion happened, right? There are so many websites being built, there are so many servers, databases, and all these big companies like Google was processing billions of web pages. It was indexing, crawling through them, and Amazon, as a e-commerce company, it was cataloging millions of products, and LinkedIn was indexing millions of profiles. And these companies, they cannot afford to wait 30 seconds for search results. Obviously, customers are going to leave the site. 30 seconds is way too much. In our current standard, even 2 seconds of delay is considered a crazy amount of delay, especially when we are talking about latency. Search results have to be very fast. We are talking about milliseconds here, right? So obviously, these big companies where they are making millions and millions of dollars every single second, they cannot afford this kind of latency. This will affect their conversion, their user base. So to solve the problem of search, the answer came from decades of research. It was not a new problem. There has been countless research in this field when it comes to text-based search and information retrieval since decades. And computer scientists have been studying how to get the results fast and keep them relevant. And researchers, scientists, computer scientists, they have been investing a lot of time and a lot of effort into it since the 1960s. So the revolution in the idea came from this particular key thought or key idea, that so instead of searching through the documents, in case of the librarian, instead of searching through the books, the title, the content, all the books, to find the relevant terms, what if we flipped the problem? What if we inverse the problem? What if we look at it in a different way? And that was the birth of this key invention, the key idea that changed text-based search forever, which is called inverted index. Now, this is a very simple concept, even though the implementation might have more complicated stuff, more mathematics, but for a high level understanding, it is a very simple concept that we are going to talk about. Coming back to our earlier example, where we think about the database as a librarian, and we ask the librarian that we want books related to machine learning, right? And the librarian goes to every book to search to the title, to the content, to the description, etc. etc. Now, coming back to the same problem, but this time we look at it using this technique called inverted index. The revolutionary idea here is, instead of going through every book and checking the existence of machine learning in those books, what if while storing the books in the shelf, when the first time the books arrive, we take all the words in that book and we create an index of those words in a way that for a particular word we can find out that what are all the books where this word is used and also where exactly it is used. For example, let's say we are talking about machine. So machine is used in this book called Introduction to Machine Learning in page 1, 15 and 23. Same way, another book called The Machine Age. Here it is used on page 5, on page 89, and another book where coffee machine manual, it is used in page 1. Same way for learning, Introduction to Machine Learning, it has been used 3 times, 1, 16, 24. Even though in a practical scenario for a book called Introduction to Machine Learning, the words machine and learning will be most likely used hundreds of times throughout the books. For the sake of this example, we are just showing 3 pages, but they are most likely used in hundreds of pages. Same way, learning to cook, it's used in 2 places, and deep learning fundamentals, it's used in 3 places. Now we have this index, which we call inverted index. So instead of going through the content and finding the terms, we have the terms, and through the terms we find the content. We just inverted the search. That's why it's called inverted index. And this technique of inverted index, this is the thing that powers Elasticsearch, a very famous tool when we are talking about full text search. Elasticsearch also has an history. It is not a completely new invention. It makes use of this technology, which is called Apache Lucene. This is the key technology, the key inverted index based technology, which Elasticsearch and a lot of other tools. Elasticsearch is not the only full text search tool. In fact, these days, even relational databases like Postgres also have support for full text search. So Elasticsearch is not the only tool. We also have a lot of other tools, full text search based tool, which most of them make use of this underlying technology called Apache Lucene, which is primarily the inverted index based text search technology. Now that is one key concept. Now that we have this inverted index, the librarian can just refer to this. We say machine learning, they can see that machine is used in all these books and learning is used in all these books. This is the first thing. The librarian and the database, we are talking about both of these things here. Just to make it more intuitive, we are talking about librarian, but you can think about database when we say librarian. Now the librarian is faster, but there is another advantage and a huge advantage, which is relevance. So from these results, we can see that for the term machine, it is used in 3 places. Now, as I said, in a book called Introduction to Machine Learning, this term machine is most probably used in hundreds of places. But for the sake of this example, it's used in 3 places. And for the book, The Machine Age, it is used in 2 places. Now, the Elasticsearch technologies and tools like Elasticsearch, they also have this feature called relevance scoring. We don't have to understand how actually it works. Understanding is good. It is definitely good to understand the underlying architecture. But again, if you just want to make use of the tool and build a service, then you can easily refer to docs, take the example and just use it. You just have to know that if you have a use case like this, go with Elasticsearch or full text search from Postgres, whatever your typical tech stack is. But you don't have to completely understand all the technologies, what is happening behind the scenes, how the index works, how the scoring works, etc. It's pretty complicated. And unless you are writing another library about Elasticsearch or creating an alternative to Elasticsearch, all that knowledge is not going to help you a lot. As long as you know the best practices, how to do certain stuff, that's pretty much enough. Now, coming back, Elasticsearch also has this concept called relevance scoring, which means that it can check the term machine is present in page 1 in the title of the book. that fact itself, that the term is present in title, it gives a significant boost to its relevance score. Now, this is the most relevant book for our query since the term is present in the title. Again, after that, we also see that it is present 3 times throughout the book. Now, that is again another significant relevance booster. It is present in the title and it is present in more frequent places. Those two things, because of those two things, this result is came on top. Same way, for this book, The Machine Age, one, it is present in the title. So that is one relevance scoring, but it is not as frequently used. So that's why it is coming in the second place. Same for the third thing. It is present in the title, but it is very less frequently used. So that's why we get it in the third place. And same logic for this term also. So as you can see, using a tool like Elasticsearch can make the experience of search fast and also give you this additional advantage of relevance based results. You just don't want any result that matches your query. You want the most meaningful result. And Elasticsearch, tools like Elasticsearch give you that feature. Now it has an algorithm called the BM25 algorithm. As I said, there is a lot of theory behind this. If you are interested, you can learn more about it. But I would suggest just treat it as a tool. Whenever you want to use it, you just know that if I have a use case like this, I have to go with Elasticsearch. Then just refer to the docs, implement the feature and move on instead of spending too much time understanding the theory. But again, if you are curious, then it's great. If you want to learn more, then Elasticsearch docs is a very good place to learn more about these things. So this algorithm that it uses, the BM25 algorithm, it has different parameters to sort the results. So one thing that we already talked about is the term frequency. How often the term machine appears in the document. How often, if we consider this book as a document, in Elasticsearch, a single entity is called a document. It's a JSON document, kind of like MongoDB. So the first category, if we see, it is term frequency, which checks that how often a particular term is present in a document. And the second category is document frequency, which checks that how common is the term machine across all documents. Right? This is in a single document and this is across all documents. Third one, document length, which checks basically how long a particular document is, if it is a short document or a long book like document. Then another thing is field boosting. Now, if you have worked with Elasticsearch before, then field boosting feature is something that we use a lot. Field boosting basically means that this term machine, if it appears in the title, then that is more relevant as compared to it appearing in the description. And it appearing in the description is more relevant as compared to it appearing in the content. Let's say for a particular book, we have a title, then that is more relevant than the description, and that is more relevant than the content. So if a term appears in the title, that is more relevant than it appearing in the description, and that is more relevant than it appearing in the content. That is what we call as field boosting. And while making a search query, we can define our own field boosting criteria. We can say that if it appears in the content, then that should be more relevant. So we can alter these things. It's not fixed. It's upon us. The Elasticsearch DSL, the language that we use, it's a JSON based query language, and it offers a lot of features, a lot of parameters to do different kinds of search. And using that, we can extract different kinds of results. So there are different use cases when we are using Elasticsearch, apart from a just basic text matching. The first one is, of course, the typo tolerance. Let's say, so I will show you an example. So we want to make Google search. Now this is a very good example. We are not sure what exactly the technology that Google uses, whether it is Elasticsearch or whether it is something proprietary that Google has built on top of Apache Lucene. But it is a technology similar to Elasticsearch, and you can build an interface like this, which is called a type ahead interface, using Elasticsearch. Right? We have this in websites like Amazon, where you type something and you get results. I want to search what is trending today. So I start to write what is. So I already got a lot of results. Now these results are scored in different parameters that depends on Google, but I want to show something else. I want to search what is trending today. So instead of writing trending, what if I write trading today? So as you can see, we wrote what is trading today. We intentionally made a typo, but because of this full text search based capabilities of tools like Elasticsearch, they can derive from the context that there is a typo, and what is trending today is the most likely intended query of the user, right? And this is a major advantage of using a technology like Elasticsearch, full text search based technology, for these kinds of experiences like typos and all, right? So if you are building a search like feature in your backend application, then you have two options. You can go with Postgres. Now Postgres, as a modern database, it also offers a full text search feature. So you can go with Postgres, or if your company already uses Elasticsearch. Now Elasticsearch is a tool, is not just used for these kinds of features like type ahead and full text search. Elasticsearch is a very famous tool which is also used in the domain of log management. So there is this very famous stack called ELK stack. So if we look for ELK stack, Elasticsearch, Kibana, and Logstack, all these three technologies combined a very famous stack for managing logs, etc. Right? Since Elasticsearch is very fast in searching things, searching through logs and deriving statistics and visualizing data, etc., there is a very famous use case of Elasticsearch. So if your company already has Elasticsearch as a part of ELK stack for log management, then going with Elasticsearch for your full text search based requirements also makes a lot of sense instead of going with Postgres. Let's go through an example of the difference between a traditional database search and an Elasticsearch based search. I have a project here. It is a Next.js based project. There is no reason for creating it in Next.js, just that LLMs are very good at generating these prototype based applications using Next.js. That's why I went ahead with it instead of writing my own in any other language. In this project, basically we have a UI like this, where we are comparing, we are executing query and running that query in a traditional Postgres based database and also a Elasticsearch instance. To keep it fair, I have created a project in Neon, serverless cloud-based Postgres instance, and a project in Elastic Cloud, right? And both the instances are situated in the region of US West. So latency because of distance should not be a big factor in our test, which or kind of benchmark that we are going to do just now. But before that, I just want to explain what I have done in this project for the purpose of the demo. I created a table called reviews in a Postgres database, in the Neon Postgres database, where the table has three fields, one ID, one review, which is a text field, and one sentiment, which is positive or negative. That is the database table. Then going to the script, which populates our database and our Elasticsearch index. I have this very big CSV file. It is around 50,000 entries of review and sentiment. I have collected it from somewhere, I'm not sure. So it has two fields. It has a review and it has a sentiment, that whether it is a positive review or a negative review, right? And it has 50,000 entries, and we want to insert it first into our database and our Elasticsearch index. So what am I doing? What I'm doing here in the populate script is, it's a Node.js script, and I'm taking the database URL from environment and Elasticsearch address and the Elasticsearch API key, right? If any of them are not present, I'm throwing an error. Then we initialize the clients. For the database, we start a Neon client, and for the Elasticsearch, we start an Elasticsearch client. This is where we are building the clients. Then we read the data from CSV. We are just doing a read file sync, and we are reading the data and storing it in this variable. Then first we populate the Postgres instance. This is our script to run, which basically says that if this table is not already existing, then create a table. But since I have already run this migration once. The table already exists. This part does not really run. Then we are just resetting the ID field so that we start fresh. Then we are doing some kind of filtration so that we have both the review and the sentiment field. If it does not have it, we're just filtering it out. Right. Then if we have valid records, then we start inserting them in batches. Since inserting them all at once has a limitation in the Neon instance, we are inserting them in batches. So we are creating a batches of 1000 and we're looping through those batches, and we are just doing a normal insert statement. Insert into reviews, review and sentiment, and just in the values, we are just inserting the review and the corresponding sentiment. And we are executing the query here. That's the database part. Then we are populating the Elasticsearch. If the index exists or not, we are checking first whether this Elasticsearch index, which is called reviews, exists or not. If it already exists, we are deleting it since we want to start fresh. If it does not exist, then here we are creating an index. And inside that index, here is how we map the fields. We are saying that we have two fields, review, which is of type text, and sentiment, which is of type keyword. Text basically means that we don't want to do any kind of discrimination around the different words in the text, but keyword means that we want to exactly match that particular word. Now again, we are checking the valid records by the present of both the fields. Then we are doing a bulk insert of all the 50,000 records in the Elasticsearch. So I have gone ahead and run this script. You can see here 50,000 documents inserted to Elasticsearch, etc. And if we check in our cloud instance, you can see that in our Elasticsearch cloud instance, we have 50,000 documents here, all populated. Same for our Neon database. So if we come here in the SQL editor, if we run this query, select count star from reviews, then we get this value, that 50,000, which means that we have 50,000 rows in our reviews table. So both the database and the Elasticsearch have been populated successfully. Then what am I doing here? This is the key part, not the UI. UI is pretty generic. The route. This is basically the API endpoint, which we call once the user types something and hits enter, runs the query. This is the API we call. So what exactly were we doing here? We are taking the search term from the JSON, and if there is something wrong with it, we just threw a bad request error. And we are starting a stream because the result timing of the database and the Elasticsearch can be different, and we don't want to delay the result of one because of the other. That's why as the results are available to us, we are just streaming it to our front end so that we can immediately see which one is faster and how much time it is taking. Right? For that, we are just starting a new stream here, and this is our Postgres search. And what are we doing? We are just starting a timer to track how much time it took to run the query. And this is the query that we are running. Select these three fields from reviews table, where review is like this search term, as I have already shown in the just a while back. This is how we typically do a search in a relational database. We use I-like because we want to do a case insensitive search to cover more breadth, and we put the percentage sign before and after the term to say that it does not matter what character comes before it and after it, as long as the term is present itself, we want to take that result. Then we have this query and we are just running it and taking all the information that comes with it, and we are just sending the result. Send result is the function which actually streams the data to our front end as the data is available, right? Second, Elasticsearch. Same thing we are doing. We are running a search through the Elasticsearch index. We have the index name here, which is reviews, and we are searching a query string. And the query is the search term. We are converting it to lowercase to cover as much breadth as possible. And whatever characters that come before and after it, we are taking that. And we are adding some default fields to enhance the search. Again, we are running it. We are executing the result and returning whatever that data comes with it. And as a response, we are saying that we are returning the stream of response as it becomes available. And in our front end, we are just reading that response as it comes through, right? There is nothing to see in the front end side. Now moving on, this is the demo. So let's say I want to run a query for the keyword laptop. Now laptop, and let's say I hit search. This is our Elasticsearch results, right? How much time it took? It took around 1 second. And our database search, it took around 3 seconds, almost 4 seconds, but 3 seconds. Now run something else. Let's say something only, and we hit search, and Elasticsearch results is already ready in 500 milliseconds, and it found around 8,000 results. And our database also found the same number of results, because to keep it fair, we are kind of keeping the search criteria the same by converting it to lowercase and matching any characters that come before and after. Because in this demo, we just want to show the speed, right? Even if we run it one more time, again, our Elasticsearch results is here in 500 milliseconds, and our Postgres search results is still running, and it took around 7.5 seconds for the database results to come. Even though the number of results is same, the time it takes is significantly larger in a relational database with the I like based syntax. So this is what I wanted to show, where you have a use case of any kind of search or type ahead, things like that. You go ahead with full text search. You can go with Postgres full text search or Elasticsearch, tools like Elasticsearch, right? There's something as a backend engineer you should have in your arsenal. You don't have to master it or anything. It is knowing the knowledge of Elasticsearch is not as important as the knowledge of database. The knowledge of database is something you absolutely have to master. You have to master how to work with databases, how to optimize them, how to understand indexes, every single part of it, because that is something that involves almost 99% of your code base as a backend engineer. But Elasticsearch is something that you can get away with just by copy pasting some snippets from any LLM or any docs. Now, of course, if you want to optimize, you have to read a little more into it. But most of the use cases, most of the examples provided in these docs and in these snippets are pretty much more than enough to cover most of the search based use cases. That's pretty much all about full text search and Elasticsearch.